Hello everyone. So today I'd like to show you a quick introduction how to solve the Laplace equation in spherical coordinates. And before that, I'd like to give you an introduction to the change of coordinate systems, or the basis system, coordinate base, which you can see here geometrically. So when I'm talking about a change of bases, you can see that you can change from your Cartesian base to any other base, which could look like this. So we're talking about a change of coordinates from Cartesian coordinates to curved coordinates and to a curved basis. And yeah, you could have like this type of coordinate systems or a skew coordinate system if you have like continuous systems on the shear stress or something. This could be a good coordinate system. Yeah, and if you want to solve a certain problem with given boundaries in a spherical coordinate system, it is obvious to solve the Laplace equation in a spherical basis system or in a spherical system. So that's what we're going to tackle in this video. But before that, before solving this equation and transforming it, or actually before solving it, I like to show you how it is transformed, and after that I will solve it in the second video. So let me give you a quick introduction to the like basis of covariant, contrariant vectors and transformations. This won't cover all the basics because it's quite difficult to cover everything in one video, and it's only to give you an overview. But if you're interested, I'm probably going to make another video on curved coordinate systems and the change of basis. So basically here are just some basics which are given. I'm not going to talk too much about it because it's probably getting more complicated, but I just made sure to write up the basics. So if you want to have a derivation with respect of the new coordinates, we will see how it looks with respect to the old one, and you could also name the coordinates u1 to u3, or in this case, in the spherical case, they will be r, phi and theta, but just in general you can name them uk. Yeah, and in the three dimensional case it will be u1, u2 and u3, as I told you. But I'm not going to talk too much about this and this notation. So actually it's just important to know that if you want to have this differential operator in the new coordinate system, you will have certain scalar factors, and the scalar factors will be as you can see here above, will relate to the derivation of your Cartesian coordinate with respect to the new coordinate. So could maybe rewrite that down here. So that's actually just an overview, but if you want to keep these factors here general, so we will have for the change of from Cartesian to a UK basis system, we'll have this relation plus is that, because we always have three coordinates x, y and z in a Cartesian system. Okay, so clear that up a bit. Okay, And that's thing here is kind of scalar factor, which I told you, which is important to know if you want to find out the derivation of dx with respect to the new coordinate system. So here you can see this will be the new basis vectors, but that's actually a vector derivation, or a derivation with respect to x of a vector r, of our vector r, which is this vector. And if you want to have the derivation instead of the coefficient, or if you want to have the derivation of respect of x in the new spherical system, it will be calculated in that way. But as we will have to transform this Laplace equation, which is not a vector equation but only a scalar value, which gives you a scalar value, we will have to know how the Vx will look in a not a vector notation but in a scalar, for a scalar value, which I will show you here further. If we go further down, so here it is. Now imagine if we have a function x, y, and z, and we want to transform x, y, and z to a new 3D basis. We will know that x will depend on these three coordinates, which could be u1, u2, and u3, but in this spherical example, it's actually known that we will have r, phi, and theta, but we could also name them differently, more generally. So let's say that we have this dependency, and now we want our first derivation of x with respect to the new coordinates. We will have to solve or apply the chain rule to solve it in the new basis. So that means we'll have df, and so that's a plus. We will have df here first divided by dr, and then dr by dx, df by d phi by dx plus d theta by times d theta by dx. The same for dy, we will just change the axis by y here, and the z's by, and the x by z for the z derivation. But for Laplace equation, we will have to apply the chain rule again to this derivation, which will actually provide us with a bunch of new terms, because we will have to apply the chain rule here, all of this chain rule, to each term, and not only the chain rule but also the product rule. So we will get a bunch of terms only for this and this one, and then we will get the same for this and this one, this and this one, and then we will all have to sum up all. I may be having an example which I can look up later to show you the exact example of the spherical coordinates. But yeah, as you can see, again, the general coordinates, if we name r more generally to u1 and phi to u2 and theta to u3, we'll get the generalized coordinates. And it is important to know that we will have a scalar factor in between those derivations. So that's the factor which actually is building up a connection between the derivation dx for old base, or the standard Cartesian base in this case, and the new base. So that's the relation. And as I told you, if you apply the chain rule on all those terms again and we'll sum them up, we will get a bunch of terms, which you can see in the general case here. So that's actually the most general case for our Laplace equation in new coordinates with those h's. And yeah, for example, if you don't have a Cartesian coordinate base, instead of x, y, and z, we could write q1, q2, q3, just in general case. And if we apply this rule again to our Laplace equation with spherical coordinates, we will get this equation. So this equation will look a bit more complicated. Just ignore this fact, because that's actually for the solution later. Yeah, I can cancel that out first, because we're first going to solve in 2D, that's why I cancel this out. But that will be the general case for the Laplace equation, which can also be described with this notation here, but that's actually something which is not that common, so it's just to shorten up everything. But that's how you get the new equation, and that's actually why you get the new equation.